Welcome to this video on ultraviolet photolithography. I am Shivakiran Bhakta from Department of Physics, IIT Kharagpur. I am accompanied by three research scholars of the Photonic Systems Lab, IIT Kharagpur, Renu Yadav, Shorbojit Mukherjee and Shubhajit Datta. Together we will be discussing and demonstrating the entire process of UV photolithography. We hope that you will get to learn something from this and you will enjoy this video. Thank you.
UV photolithography, we use light to write structures or to make structures on a substrate. So here we are using OAI200 model for writing this microstructures on a substrate. We have this part is the light source in which we can use two wavelength. One is 365 nanometer and another is 405 nanometer. We place our substrate on this translational stage which can move in X, Y and Z direction. This is also called mask aligner. So what we do is that we use vacuum pump to hold the substrate and then we place our mask over it and then we take it and expose under the UV light. Now for photolithography process, we actually need to take care of two things. One, the room should be of positive air pressure. Number two, the light should not react with the photoresist material which we are coating.
So now we will look at the steps involved in the photolithography process. So the steps involved are substrate preparation, coating the photosensitive material, soft baking, exposure with light, development, hard bake and photoresist removal. We will look at each of these processes in detail. So first step is substrate preparation, which consists of three steps: substrate cleaning, desorption of water and treatment with adhesion promoters. So before coating the substrate with the photoresist material, it needs to be cleaned thoroughly in order to remove any dust particles or organic contaminants present over the substrate. In order to clean the substrate, we mix the ethanol and DI water and we place the substrate in it and ultrasonicate it for few minutes. Then it is rinsed off with DI water and dried using a nitrogen gun. Next, in order to remove the water adsorbed on the surface of the substrate, it needs to be heated at certain temperature. So generally we heat it at around 100 degrees Celsius for few minutes. Next step is treatment with adhesion promoters. Now, while we are treating our substrate with this ethanol and DI water, the surface can become hydrophilic. But if our photoresist is hydrophobic, in that case, the layer will not be formed uniformly. Then we need adhesion promoters, for example, HMDS and T prime. But in general, adhesion promoters, they are not recommended because for the post photolithography processes such as lift off and etching processes, these chemicals can actually prove to be fatal. So in general, we don't use this and we won't be using them in our lab too. Next step is coating this clean substrate with the photosensitive material. So now first let us look at what a photoresist or photosensitive material is. A photosensitive material is a light sensitive polymer which on exposure to light loses or gains its resistance to etchant or solvent. That is, when this photosensitive material is exposed to light, its chemical properties changes. It is of two types: positive photoresist and negative photoresist. Now let us look what is a positive photoresist and negative photoresist. In positive photoresist, areas exposed to light become more soluble in the developer while unexposed resist areas remain on the substrate. While in negative photoresist, the areas which are exposed to light, they harden and they become less soluble in the developer due to cross-linking. Now let us look at what is the basic difference in the photolithography process when this positive and negative photoresist is used. So we have the substrate over which the photoresist material is coated. We have the mask with the desired pattern which is placed over this substrate. Then it is exposed to light. After the exposure, the structure is actually put in the developer. And after development, we can see the final structures formed. Now, if we look at this, in case of the positive photoresist, the structure transfer are similar to that of the mask, while in case of negative photoresist, the structures developed are actually the inverse of the photomask structure. Hence, their name, positive and negative photoresist respectively. Now these are the example of some of the commonly used photoresist. In our lab, we are using a positive photoresist AZ4562, and comparing the positive and negative photoresist, one main characteristic which needs to be kept in mind is the minimum feature size or the resolution which could be attained. If we see from here, for all the other optical parameters or photolithography process parameters kept same, we see that the resolution which could be achieved for the negative photoresist is less as compared to the positive. This happens because the cross-linked polymer in case of the negative photoresist, that can actually absorb solvent from the developer and it can actually swell. And due to this swelling process, the resolution which could be attained is actually limited. So once we have our clean substrate and we have an idea about the photosensitive material, we need to coat it over the substrate. So there are various coating techniques available: spin coating, spray coating, and dip coating. Spin coating is one of the most commonly used method, and we are using spin coating in our lab too. So in spin coating method, few ml of the photoresist is dispensed on the substrate and it is rotated at high RPM for several seconds. Due to this rotation, the uniform layer of the photoresist is formed over the substrate. While developing the structures like microarrays and micropillars, the thickness of the resist film can actually affect the height attained. So we need to look at the parameters which can actually control the film thickness. So these parameters are attained spin speed, spin time, temperature, and equipment. So from this diagram, we can see as the spin speed increases, the centrifugal force increases, and hence the resistance thickness that could be attained it actually decreases. Same happens with the spin time. So if the spin time is more, in that case the resistance thickness will be less. The temperature and the equipment actually refers to the environment. So if the temperature is more, that will actually lead to faster rate of evaporation of the solvent, and hence the film will be thinner. By equipment we mean the environment inside the spin coater. So if the air inside the spin coater is more humid, so that will actually affect the rate of evaporation and hence our resist film thickness. So the next process involved is soft baking. So why this is needed? So after the coating, the resist film might be having residual solvent concentration of 10 to 35% depending on the film thickness and the solvent used. So in order to get rid of this solvent concentration, we heat the coated substrate at around 100 degrees Celsius either in the hot plate or the hot air oven as shown here in the figure. Now, what is the benefit of this actually? So in order to, we use it in order to avoid the contamination of the photo mask with the resist as well as mask sticking to the resist, in order to improve the resist adhesion to the substrate and to allow multiple resist coating without dissolving the already coated resist film by the next one, and also to increase the stability of the resist structure. So the next step is exposure with light. So now we have the photosensitive film coated over the substrate and we need to expose with suitable light in order to develop the structures. So before that, we will look at some of the other things like what is a mask and what are the UV light sources which are being commonly used, and the two important parameters which are being used in the photolithography: the exposure dose and the exposure time. So what is a mask? A photo mask is an opaque plate with holes or transparencies that allow light to shine through in a defined pattern. Lithographic photo masks are typically transparent fused silica blanks covered with the pattern defined with a chrome metal absorbing film. For example, one image is shown here of a photo mask. So if we can see that the structure is written with the chromium material, and from these black regions the light cannot pass and it forms the image, and all these white regions the light can pass. So hence if the light falls on this photo mask, so we can see that it forms the image of the structure which is coated over the mask. Now there are various photolithography sources which are being used like mercury lamp, fluorine laser. In our lab we use the mercury lamp, and which can actually give three wavelengths: 436, 405 and 365. In our lab 405 and 365 nanometer are available, and we will be showing you by using the wavelength of 365 nanometer. If you look at the last column, we see that as the wavelength of the source actually decreases, the feature size that could be attained actually also decreases. That means with lower wavelength, higher resolution could be attained. But as we go in the deep UV region, the optics becomes costly, and hence in order to compensate that, we try to use the wavelengths like 405 and 365. So the next step is in the exposure of the light, we need to have an optimum exposure dose and the exposure time. So as we can see from this figure, so this is an example of a thin resist film, and this is an example of a thick resist film. So now when a thin resist film is exposed to the light, and we with the time we can see that the structure is being exposed and a uniform exposure happens. That is it is homogeneously exposed. But in case of the thick photoresist films, what happens, it is not homogeneously exposed, and we see that as we keep on exposing it with the time, so it increases layer by layer, and finally after sufficient time it is fully exposed. Hence it is very crucial to decide the dose as well as time. Now one interesting thing is that this dose and the exposure time, they are actually interchangeable. So that means we can use a higher dose for a shorter time, or a lower dose for a higher time. So this flexibility is actually being also used in our labs. Now, as we saw in the earlier slide, that the lambda actually controls, that is the wavelength of the light actually controls the resolution that could be attained. So which is also being shown by this equation. So the latent resolution that can be attained is dependent on the wavelength of the light and the gap between the mask and the photoresist film. So when we have this photoresist film over the substrate, we need to place the mask over it. Now, if there is a gap between the mask and the photoresist film, that can actually also affect the minimum feature size that we can attain, and this is shown by these two figures here. So first is the example, so it is related to the diffraction. It shows the diffraction of the light. So as the size actually of the slit is actually becoming smaller, the diffraction is more and more prominent. And this lower figure actually shows how with the variation of the gap between the mask and the photoresist film, the distribution of the light intensity over the resist film changes. So we see in the first case the gap is 0, and this is a distribution of the light, and as this gap actually keeps on increasing, so that is how the distribution of the light over the resist film changes. So we see that as the gap is more, in that case there is a more non-uniform distribution of the light as compared to the case when the gap is actually nearly 0. Hence it is very important to see that what is the gap between the mask and the photoresist film. So the next step is development. So after the exposure, a latent image of the mask is formed in the photoresist. The exposed areas differ chemically from the non-exposed areas, and development dissolves either the exposed for positive photoresist or the unexposed for the negative photoresist areas, resulting in the final desired resist structure. So there are different types of developers that can be used. For example, aqueous alkaline developers like KOH or NaOH. So in our lab, we use KOH, and some other organic solvents like ethanol, acetone, etc. can also be used. So here this animation shows how the development is done. So in a petri dish, we put the developer and we put the exposed structure in that, and then it is shaken for some time, and after that actually we get the final structure. Now, one important thing that need to be kept in mind while choosing the developer is that the developer need to be compatible with the photoresist, and optimum degree of the dilution and the temperature need to be chosen for the better development. So we will see how these factors like dilution and temperature are affecting. So in this figure, if we see, so we actually dilute the developer with the DI water in the ratio. So as this ratio is changing, that means as the dilution is changing, we can see that this development rate is also decreasing. So if it is very dilute, the development rate will be very low, and it need to be kept in the developer for a very long time. In the second figure, for example, we see for AZ4562, that is the photoresist we are using, so it is very temperature sensitive. Hence, it is mandatory to maintain a constant temperature while developing, otherwise the development rate can change. That means it can fluctuate, and that can actually lead to the either the over dissolving or the less dissolving of the structures. But for some other photoresist, for example, shown here AZ726 MIF, for this the development rate is actually independent of temperature. So depending upon the photoresist we are using, we need to keep in mind also the temperature where we are developing our films. After developing the films, the next step is hard bake. So in the hard bake, the structure is actually heated at around 100 to 140 degrees Celsius for several minutes, as shown here in the figure. Now, hard bake is an optional step, and it may not be mandatory to be carried out, but it is actually helpful to make the structures more stable by subsequent physical or chemical processes like wet or dry etching, etc. So the next step is photoresist removal. So there are two reasons why we need photoresist removal. So first one is that either we need to use the reuse our substrate, so in that case we need to remove the photoresist. And the another thing is that, so these structures developed by photolithography, they are actually the first stage of the device fabrication. After that there are various processes involved in order to make the devices. So for example, lift off technique is there, etching is there. So for that the photoresist need to be removed, and there are various photoresist removers which can be used like acetone, NMP, DMSO, and KOH and NOH, as well as some ready-made strippers like AZ100 remover, etc. are also available. Photolithography is an initial step for the device fabrication. Post photolithography, there are various techniques which are used to make the devices. One example is soft lithography. In this, the structure fabricated by photolithography is used as a master. An elastomer, most commonly used is the PDMS, is actually poured over this and peeled off. After peeling off, we get an inverse structure which is made up of this elastomer, and this elastomer actually can be used as a stamp. So here we see there is a substrate over which a thin layer of a material is coated, and this, using this replica mold as a stamp, this structure can be transferred. So this process is called soft lithography, and it is actually much more feasible than photolithography, because one stamp can be actually used for multiple times to make the structures. So two other processes are lift off and etching, which are shown here. So in the etching process, the substrate is actually coated with the metal, and over that the structures are developed using the photolithography technique, and after etching the structures are transferred over the metal layer. In case of lift off, first the structures are developed over the substrate using the photolithography process, and over which the metal is coated, and after then lifting of this photoresist using this photoresist removal, the structure is again transferred over the metal coating. Now, so we learned about photolithography, what are its application, what are the steps involved, and how it can be used for other device fabrication. Now let us look at some of the limitations of this photolithography method. So one limitation is a diffraction. So as we saw, like the lambda that we are using, the wavelength that we are using, it actually leads to the diffraction if the sizes of the structures, they are comparable to that of the wavelength. So that is one of the important limitation which actually limits the resolution that could be achieved using photolithography. So using the photolithography, that setup that we have in our lab, we have reached to up to a resolution of around few microns, around 3 to 5 microns, but it's not possible to go beyond that with the current setup. The another thing is that if we want to achieve the smaller feature size, then we have to use the wavelength of the light, which is actually smaller than we are currently using. But that as we go in the deep UV region, that actually leads to the changes in the optics that we are using, and the optics that can be used in deep UV region is quite expensive. And another limitation is like it is more suitable for the flat surfaces. So if the substrate that we are using is actually curved, in that case the photolithography process has some limitations over the resolution that could be achieved. Here are some of the images of the structures which we fabricate in our lab. So first two images are that of the microfluidic device that we fabricated using the photolithography techniques. So this first structure, it actually consists of the circles of diameter around 20 microns, and then we see that the structures are formed very well. This is the example of a microfluidic channel of diameter around 100 micron, and this third figure is that of a WGM resonator that has been fabricated using the photolithography technique.
So now we are going to coat photoresist on a glass substrate. So this is a glass substrate which has been already cleaned using ethanol and DI water in ultrasonicator. So we actually somehow ultrasonicate it for 5 minutes. So this is a clean substrate. So which we will be putting on the chuck in a programmable spin coating. This is a photoresist AZ4562. Will few ml of photoresist will drop using the injector. This is a photoresist injector.
Now we are going to drop a few ml of photoresist gently on the glass substrate, which is tightly held on the spin coater chuck.
Will on the vacuum.
We have to close the lid and start the spin coater, in which the angular speed and the spin time are already programmed. The set time is over. Now we are opening the lid and we see the rotating chuck deaccelerating and coming to a standstill. Generally, we should open the lid only after the sample has stopped rotating. We are taking out the photoresist coated substrate from the spin coater and you can see a thin layer of photoresist on the glass substrate. Now we are going to place it in the oven set at 110 degrees Celsius for 12 minutes.
To expose the substrate, so we need a mask. So this is one of the masks we are going to use today. So this is made of fused silica over which chromium is written, which is going to be the structure. So this is the soft baked substrate, and we can see it has a slight color change from brownish to yellowish. Now this substrate is ready for the exposure. So now this substrate will be put in the mask liner where the substrate holder is already present. Now here this pipe is connected to the vacuum. I am going to put this photo mask on over the substrate. Now I will adjust the 3D stage so that the photoresist is touching with the photo mask. The whole stage I will move it to the exposure chamber to expose. So I am slightly moving.
Now we move the mask liner stage into the UV exposure chamber. As soon as the sample is pushed in, the UV lamp turns on automatically. The photoresist coated substrate will be exposed under the UV light for the preset time. The wavelength of the UV source is 365 nanometer.
Now this exposed substrate will be taken for developing.
We are removing the photo mask placed over the coated substrate. Then the exposed substrate is taken to immerse it in the developer already present on the mechanical shaker. The diluted KOH solution developer was kept in two petri dish. In one of them the substrate is dipped and the other one is kept as reference to see the color change. We have to wait for a few minutes to see that.
The color change of the solution. So previously it was completely transparent, as you can see, and now it has been changed the color. We will wash our substrate with dry water to see how the structure is coming. Let's see.
Since the structures are very small, having dimensions in micrometer, a microscopic image is shown of that fabricated structure.
UV photolithography has wide application. It is used in microprocessor industry to make processors which are used in our phone, laptop. It is also used to make microcontrollers. It is also used in the field of biology to make lab on chip where micropillars, microwells, microstructures are also made. In field of communication, it is used to make waveguides, and also it is used in sensing where disc resonators are used for sensing. So we can see that UV photolithography has wide amount of applications. Hope you enjoyed the video. Thank you.